you, Samson. Thanks to the conference organizers for giving me this opportunity. Thank you all for coming. So I'm going to talk about some new results I am seeing on the cohomology of contextuality. So when I wrote this paper, I thought there was actually only one approach to cohomologically study contextuality, but it turns out in this conference that probably a more appropriate title would have been on a cohomology of contextuality. So just to make it clear, this is based on the very first paper on the cohomological study of contextuality by Samson, Rui, and Shane, who are all here today. So this is a sort of follow-up to that paper. So I'm going to briefly outline what I'm going to talk about. So I will start by briefly recalling some of the main definitions of the sheaf theoretic description of contextuality that Kohei talked about in the tutorial on Monday. I will then also briefly mention some connections between the study of contextuality and the study of impossible figures in topology, and why that motivates our cohomological approach to contextuality. I will then move to sort of the core of the talk and consider check cohomology as a tool to detect contextuality, and especially consider some new results on how powerful this method is. I will present a generalization of the cohomology obstructions to higher cohomology groups. And finally, I give an alternative description of the first check cohomology group using Torsors. So it will become hopefully clearer why these things are important during the talk. If I still have time, I will talk about some future research. As Kohei explained on Monday, there has been this recent work by Samson and Brandenburger that used sheaf theory to characterize non-locality and contextuality in a unified approach. So this has been explained before, so I'm not going to spend too much time on it, and I will basically introduce it using the natural basic setting that has been presented many times in this conference. So we have what we call the 2-2-2 bell type scenario with two agents, Alice and Bob. Alice can choose between measurements A1 and A2. Bob can choose between B1 and B2. So this diagram summarizes one run of the experiment. So in this case, Alice has chosen A1 and Bob has chosen B2. And this choice sets what we call the measurement context. So the measurement context is A1, B2, and it is one of the maximal sets of measurements that can be jointly performed. Now they do their measurements, they obtain 0 for A1 and 1 for B2, and now we can summarize this whole event using this function that assigns to A1, B2 the outcomes 0, 1. So this function or section in sheaf theoretic terms. So such a scenario, and every scenario actually can be described abstractly using mathematical objects. So we define a scenario using a triple constituted of X and O, where X is a finite set of measurement labels. So in our case, it's just the set of all the measurements we have, A1, A2, B1, and B2. And for convenience, we turn it into a discrete topological space. So we just put the discrete topology on it. We then have M, which is a finite cover for X, which contains all the contexts, so all the possible choices of measurements that Alice and Bob can make. And finally, we need a set of outcomes for the measurements. So in our case, it's dichotomic measurements, so the set of outcomes it's just 0 and 1. So to every measurement scenario, we can associate a sheaf, which we call the event sheaf. And this sheaf associates to every subset U of the set of measurements X all the events on that subset. So it takes all the functions from U to the set of outcomes. And it's quite easy to see that this verifies the sheaf condition, so it's actually a sheaf. So there is an alternative description of a measurement scenario that uses abstract simplicial complexes. So in this case, vertices of the complex would be measurements. And we have a set of vertices will constitute a face of the complex whenever the corresponding measurements can be jointly performed. So in our case, in the 2-2-2 bell type scenario, we have like a square of the measurement complex is in a square shape. Okay, so now we've defined what a scenario is. We can define what an empirical model is on it. So we can actually perform the measurements on an actual physical system. So we define a no signaling, a probabilistic empirical model as a compatible family of probability distribution on the events on each context. So this compatibility condition is not really important in this talk, but it's basically no signaling. I think Rui has already explained this in detail. So this is sort of a technical definition, but we can actually see it in a more straightforward way using probability table. This is exactly the same table you've seen just a few minutes ago. This is the Bell model, and so you can see that there are probability distribution for each context. Each context is one row of the table. So in this talk, when we study contextuality, what we're interested in is whether there exists a global probability distribution that marginalizes to explain all the entries of this table. But in this talk, we're not really interested about probabilities. We're more interested in possibilistic models. So we don't really care about how the probability of a certain event to occur, but only on whether it's possible or not. So one way of obtaining a possibilistic model is by taking simply the support of the probabilistic empirical model, like I did in this table, and we obtain a possibility table. And studying contextuality in this framework means that we're trying to find whether there exists a global assignment that explains the entries of this table. So by abstracting from this situation, we can define empirical model, possibilistic empirical models more axiomatically within sheaf theory. So we say that a possibilistic empirical model on a scenario XMO is a sub-presheaf S of E such that the following conditions are verified. The first condition is that, well, we have at least one possible section for every context. That's because otherwise it wouldn't be very interesting to study that context. The second condition is a bit more technical. It's called fluxidity beneath the cover, and it basically says that the restriction maps of the presheaf are surjective below the cover. So this can be interpreted as a possibilistic version of no signaling. So this is what counts. And finally, whenever we have a compatible family of sections above each context, and here by compatibility I mean that they agree on intersection, then that family induces a unique global section in S of X. We have this correspondence between compatible families and global sections. And again, the global section, I insist, is what we're interested in, is determining whether there exists a global section that explains the entries of the possibility table. So we can now define contextuality. We say that a model is logically contextual or possibilistically contextual at a certain section S, if S is not a member of any compatible family. And by the third condition, this means that S cannot be explained by a global assignment. So there's not a deterministic way of explaining this section. And if that's the case for all the sections of the context, we say that the model is strongly contextual. Okay, so we have a very nice representation, graphical representations of possibilistic empirical models. Kohei has shown this before, and Rui too, so I'm not going to talk about it too much. So we just have the measurement cover lies at the base of the diagram, and above each vertex, each measurement, there is a fiber of outcomes for that measurement. So in our case, it's just 0, 1. And we define a possible section by simply highlighting an edge in the picture. And what's important is that global assignments correspond to closed loops on the bundle. And it's important to notice that we're only allowed to go around the bundle once. We cannot do double loops. Okay, so I think I'm going to skip this. It's not too important. So here's an example. Why bundle diagrams are important is that if the model is simple enough to be graphically represented like this, it can give us a very nice way to have an immediate feedback on the contextuality of the model. So here is the Hardy model. Here are all the possible sections. And by simply looking at the diagram, you can realize that this model is logically contextual or possibilistic contextual, but not strongly contextual. And that's because if we look at the red section and try to extend it to a closed loop, you always fail. But there is a global assignment there. Like the blue section, for instance, is part of a global assignment. So the model is possibilistically contextual, but not strongly contextual. On the other hand, if we look at the PR box model, which is represented in this way, you can see quite easily that there is not a closed loop. The only way you can obtain a closed loop if you go around twice, but that's not allowed. We're only allowed to take one section above each context. Okay, so by showing you this sort of topological representation, topological fiber representation of models, I hope I can convince you that, in fact, the study of contextuality is not very different from the study of topological properties of this kind of topological representation. And in fact, there is an even more interesting connection with topology. So it has been argued before that, in fact, the study of contextuality is very much about the discrepancy between local consistency and global inconsistency. This discrepancy has been studied before in topology, namely by Roger Penrose. So here's a picture from his paper on the cohomology of impossible figures, which I encourage you to read. It's like 3 pages long. It's very accessible. There's no requirements for understanding it. And if you look on the left-hand side, we have a trivar, which is a figure that cannot exist in 3 dimensions in our reality, basically. And if we look at the picture globally, you immediately realize that it's not, there is a contradiction. It cannot exist, such a thing. But if we look at the right picture here, and we divide this figure into 3 regions, or I should say in 3 contexts, then by simply looking at locally at one of the contexts, there is no contradiction there. Everything works fine. And it's only when we try to glue things together that we realize that it's actually, there is a contradiction there. So Penrose studied this kind of properties using cohomology theory, and in particular check cohomology theory. So that kind of motivates why we use check cohomology theory. And also, of course, well, the main motivation is that we've used this sheaf theory to describe contextuality, and therefore sheaf cohomology, which is already a tool that is used in algebraic geometry and algebraic topology to study extendability from local to global. Then, of course, it makes sense to use this also in this context here. Okay, so as I said, this talk is mainly based on the first paper on the cohomology of contextuality by these guys here, who are all here. So I want to summarize their results and set the goals of this of my work. So the first result, the most important one, is that cohomology obstructions in the first check cohomology group provide a sufficient condition for contextuality. So cohomology can indeed witness contextuality in empirical models. However, this condition is not necessary. There are some false positives, as also Frank has just talked about. But they also pointed out that cohomology works particularly well for strong contextuality. So it seems to detect strong contextuality very well in all the well-known quantum models. So my goal is to give an answer to some of the open questions that were left by that paper. So the first one is, since cohomology works so well for strong contextuality, is there a way to characterize what cohomology actually detects? In other words, is the cohomology obstruction a full invariant for strong contextuality, provided that we give some reasonable assumptions on the measurement scenario? Secondly, as I said, here this approach, and I think also the approach we've seen from Robert and Frank, except the second, you use the second cohomology group. All the approaches we've seen is that they only involve one cohomology group, and a natural question is, can we use higher cohomology to have more information on the model? And finally, so these obstructions here are quite obscure objects. They're defined by very strange relations that are imposed by the strict definition of cohomology, and therefore it would be very nice to have a concrete explanation on what these things are. And this is what I'm going to talk about in the rest of this talk. So how does cohomology work? This is just a few, I will skip most of the technicalities. So we start with an empirical model S given as a presheaf on a scenario. The first issue we have when we try to define check cohomology is that we need a presheaf of abelian groups, and we only have a presheaf of sets. So the reason why we need a presheaf of abelian groups is mainly that the abelian group structure of the cohomology groups is inherited by the abelian group structure coming from the sheaf, the presheaf. But from a more concrete point of view, there's also a concrete reason why we want to do this, and it's basically because when we try to study contextuality, all we care about is finding this compatible family. So we need to have a way of comparing sections at the intersection of contexts. And a sensible way to do this is defining some sort of difference between sections. So what we do is we give a composition law, and then we can define differences between different sections. So what we do in practice is that we simply take the free abelian group generated by each set, and this allows us to take formal linear combinations of local sections above each context. Then here we define the check cohomology of F with respect to the cover M. Here, I'm sorry, I have to skip all the definition of the check cohomology. I'm very grateful to Frank for his very nice, intuitive definition of what cohomology actually is, so that I don't have to talk about it too much. And then what we do is we associate to every local section of a certain context C a cohomology obstruction, gamma C of S, inside the first check cohomology group. And then we define the notion of cohomological logical contextuality. So we said our model is cohomological logically contextual at a certain section S if the obstruction does not vanish. It's not zero in the first check cohomology group. And if that's the case for all the sections, we say that the model is cohomologically strongly contextual. And the main theorem that they obtain is that, well, this is a sufficient condition for contextuality. So cohomological logical contextuality implies logical contextuality, and of course that's also true for cohomological strong contextuality. Okay, so I mentioned that there are some false positives. Here I'm going to show you one, and then I'm going to show you why such false positives arise in cohomology theory. So here's the Hardy model. We've seen this before, and we also saw that if we try to extend this red section here to a closed loop, we fail. As you can see, this is the only possibility we have, basically. But now, from the cohomology point of view, we're allowed to take formal linear combinations of sections above each context. So what I can do, I can subtract this section over here, and then add this section over here, and we do obtain a closed loop. So of course, from our perspective, this is not a valid closed loop, because we are only allowed to take one section above each context. But for cohomology, this is perfectly fine. So cohomology doesn't detect contextuality in this case. But as I said, cohomology works very well for strongly contextual models. It can detect strong contextuality in GZ states, pure boxes, Fermi magic square, all non-GCD models that were described in a previous paper by Samson, and I think this was the same paper I cited before. And the whole class of models submitting all versus nothing arguments. There's only one known example of a strongly contextual false positive, which is the Cohomological model for Discover here, which has some strange properties. It was sort of constructed ad hoc in order to obtain a false positive. And Discover does not satisfy any reasonable criterion for symmetry or any strong form of connectedness of the cover. And in particular, the existence of measurements that belong only to a single context seems to be crucial in constructing this this counterexample. This is a quote from the original paper on cohomology. So they formulated this conjecture. So under suitable assumptions of symmetry and connectedness of the cover, the cohomology obstruction is a complete invariant for strong contextuality. And unfortunately, I show that this is not true. I give a counterexample. This is the bundle diagram of the counterexample. This is a strongly contextual model that is absolutely cohomologically non-contextual. defined on a very simple measurement scenario, namely a 2 to 4 bell type scenario that satisfies any reasonably strong form of connectedness and symmetry properties. So I'm going to give you a very simple proof of why this is a counterexample. In fact, you could just look at the diagrams. So on the left-hand side, take this red section over here and try to extend it to a closed loop. On the left-hand side, I show you all the possibilities you have to extend it, and you always fail. But on the right-hand side, we have this kind of cohomology loops that work very well for cohomology. So cohomology cannot detect contextuality at this section over here. So, and this works for every section of the model. Here's another example. I take the red section over there, I try to extend it to a closed loop, and I fail. But cohomology can do that by taking linear combinations. And here's another example where I need to do some more work with cohomology. So it looks like we cannot quite characterize what cohomology detects in physical terms. I mean, it's difficult to give a physical interpretation of what does cohomological contextuality mean. And so, I mean, the thing is, there is no good reason why we should have this kind of characterization, because after all, we've defined contextuality in general mathematical terms. So this is just a property on its own. Okay, so I'm now going to switch gears and talk about the generalization to higher cohomology groups. So, as I said, the theory developed so far only involves the first check cohomology group. So a very natural question is, can we use higher cohomology groups to study, to obtain additional information? And I obtained the following results. So the first one is that obstructions can indeed be generalized to higher and remarkably only to odd-dimensional cohomology groups. I'm going to show you why. And we can actually use this generalization to refine the notion of contextuality into different levels of cohomological contextuality. And the nice result we obtain is that these levels are organized in a precise hierarchy of logical implications. But there's also a bad result, which is that we cannot use this hierarchy to study no signaling empirical models. No signaling is too strong in a certain way. So I'm going to show you now basically the main idea behind this generalization. So let's start by seeing what happens with the base case with cohomology, what we know so far. So how do we define the cohomology obstruction inside the first check cohomology group? Well, we take a section at a local section inside in a certain context, and what we do is that we use this blue isomorphism to encode that section as a cocycle, as a zero cocycle inside Z0. And then we use the long exact sequence of cohomology to define the cohomology obstruction. So here's a picture that Koei showed before. This is exactly what happens. So we start with a local section. We start with a local section in f of c, which represents a section in s of c. We encode it as a cocycle here, and then we take this connecting homomorphism that it's already built inside the cohomology theory. So the nice thing is that if we consider this blue isomorphism as an injection inside the group of zero co-chains by simply taking the inclusion, then this isomorphism, this inclusion, this injection can be generalized to arbitrary dimension in an injection, but what we're really interested in is whether we can, this function factorizes through the group of cocycles. And this turns out to be true only when Q is even. So it's only, we can only find a higher dimensional counterpart of this isomorphism here only in even dimension. This map here generalizes this one, but only in even dimensions. So as a result, we can define higher obstructions only for odd-dimensional cohomology groups. And this is how it works. So again, we start with a local section here. We encode it as a co-cycle in an even dimensional higher cohomology group. And then again, we take the connecting homomorphism of the non-exact sequencing cohomology that is already there for us. Everything else generalizes quite nicely. Okay, so using this new general version, we obtain a refinement of the notion of cohomological contextuality. So we can define, as I said, the higher cohomology group as this composition of the blue arrows. So this gives us the higher higher cohomology obstruction. And then we can define the notion of cohomological logical Q contextuality, and we say that the model is cohomological logical Q contextual at the section S whenever the Qth obstruction does not vanish. And we do the same as before for strong contextuality. So the nice theorem we obtain is that these levels of contextuality are in fact organized in a very precise hierarchy of logical implications. So what happens there is that if a certain obstruction vanishes at order Q, then it vanishes for any other higher order. And this is quite nice. It's nice. It's a nice mathematical result. And there's no such thing in the mathematical literature. But unfortunately, for our case, it doesn't work very well because nothing is gained for no signaling empirical models, because I prove this proposition which says that no signaling empirical models are always cohomologically Q non-contextual for any Q strictly larger than 0. So basically, everything from here to the right is useless in our case. So basically, this is to say that we cannot really use, or at least there's not a natural way of generalizing our framework to take into account higher cohomology groups.
To be wrapping up in a moment.
Yeah, okay, so, well, the last result is about how to describe the first check cohomology group, which is the one we're interested in at this point because it's the one that contains the obstruction in a more concrete way. So yeah, I'm going to skip this. This is just it's not really important. So a nice way of doing this is by using Torsors. Torsors model very well the elements of the first check cohomology group, because what we're trying to do, it actually makes sense to use Torsors, because so Torsors are a way of accounting for differences inside a certain group. So for instance, there is a very nice note on the internet from John Bates that explains Torsors very well. It's called Torsors Made Easy. And it basically, it starts from very simple physical examples. Like for instance, in physics, we cannot really talk about energies in an absolute sense. We can only talk about differences of energies. So in a way, a Torsors is just a group that has forgotten its neutral element. And if you think about it, what we're doing with cohomology is exactly the same. What we're interested in is the difference between different sections at the intersection of contexts. We don't really have a way of speaking about this in a general sense. So yeah, here is a definition of what a torsor relative to a presheaf is. It's not really important to understand it. This is just technical definition. It's important that you get the intuitive result. And the main result is just that we obtain an isomorphism of group between the group of torsors and the first check cohomology group. So this is a very nice way of characterizing the first check cohomology group and therefore the cohomology obstructions. So yeah, this is the punchline, is that torsors are very nice and are very well behaved. Sorry if the last part was a bit fast, but thank you for your attention.
Any questions?
Yes, you have a concrete description of the first cohomology group, and you have this hierarchy that gives some connections between the first cohomology group and the higher cohomology groups. So could this be used to also obtain a more concrete description of the higher?
Yeah, well, actually, so this is sort of an adaptation of a certain result that exists in general cohomology theory, and actually there is a more defined connection between cohomology and not Torsors but gerbs. So you can describe higher cohomology groups using gerbs, and I haven't done that, but I was definitely on one of my plans to look into that more carefully. So, yeah.
Okay.
Thank you.
This counterexample to the symmetry thing, so the 4-layered one. How did you build it?
I just by taking I was just playing around with bundle diagrams. So, yeah.
Just magic again.
Yeah, just magic.
But it's sort of illustrates the fact that bundle diagrams are a good way of
Exactly, yeah,
visualizing.
exactly. That's a perfectly good example of why bundle diagrams are useful too.
So about this example as well, do you know anything about quantum realizability of it?
No, I actually doubt that it's going to be quantum realizable. I don't think so, but it would be interesting to see if it's actually realizable.